So we know that the definite integral from a to b represents the net accumulation of a function over an interval. So this means that the definite integral also represents the net area bounded between the curve and the x-axis. And we say it that way, like the net area, because remember that area under the x-axis is considered negative. So typically when we do a definite integral, right, you're negating anything that's under the curve. So typically we're just using it between the curve and the x-axis. So we can kind of extend this idea to thinking about how to find the area between two curves. So if we think back to Riemann sums, we used to find the area under a curve by partitioning up the region into rectangles, right? And you would want to find the area of each rectangle and then add them up. And we used a sigma notation, right, a summation for that. So we would do the base of each rectangle, delta x, right? So here would be like a delta x, right? So it's the same as the width down here. And then we would want to multiply that times the height. So in this case, that would be right, this line here. So in this case, that would be the top function, f of x, minus the bottom function, right? The difference between them is the distance between them. So as we let the width of the rectangles get infinitesimally smaller, right? So as we let the delta x, not as it goes to infinity, but as the number of delta x's goes to infinity, right? We actually get this, right, that we get infinitesimally narrow rectangles, so it becomes a dx. So we can get that the area between two curves is just going to be the definite integral of the top function minus the bottom function dx. So we always want to remember some things about area, right? Area is always positive, so we want to be careful that we're not getting any sort of negative answers out of it. That means that we set it up wrong. So in order to make sure we always have positive area, we want to make sure that the heights of our rectangles stay positive. And we're going to do that by having the bigger function minus the smaller function. Okay, scroll back down. Right, depending on how your functions are given to you or how they kind of look, there's sometimes easier ways to do this. So we can simplify this idea of bigger function minus smaller function to being the top function minus the bottom function for a vertical rectangle. So this would be a dx integral. Or if you want to rotate your rectangles and have them be horizontal rectangles, that would make this into a dy equation, dy integral, because the bottoms of your rectangles will be across the y-axis versus the x-axis. And then that's just going to be the right minus the left function. So just something to be aware of is that the functions intersect and the order needs to be changed. You simply need to split it up into multiple integrals. So you always want to pay attention to what function is on top over that interval that you're integrating over. Is it always the same function on top, or does it change at some point? Always something to be aware of. So we're going to go through 4 basic examples. We're going to use the calculator for some of them, and we're going to do some of them without the calculator, just kind of to show how you can do it both ways. But before we do that, write some just basic tips for success here. You want to sketch a graph or use a graphing calculator if you're allowed to make a picture of it. So that way it really helps to figure out what function is larger over the interval. And that's, of course, if you're not provided with a graph. From the graph, you might have to identify your own region that you want to find the area of if the bounds are not explicitly stated for you. So that's just going to be the intersection points. Between the two curves. And then you want to determine if it's going to be easier to use vertical rectangles, which would be a dx, or horizontal rectangles, so it would be a dy, right? And I find that it really helps if I draw a representative rectangle on my sketch or graph because it helps me to correctly set up the height equation so I make sure I'm not putting it in the wrong order. Okay, so the first example we're going to look at, we're not going to use a calculator for. So we're going to let R be the region bounded by the functions f of x equals x squared minus 2x and g of x equals 8. And it says as shown on the diagram below, but I decided to not put the picture here just to practice making your own picture without a calculator. We want to find the exact area of the region R without using that calculator. So one thing that helps to help sketch it is I'm going to factor out my f of x equation, so that's x times x minus 2. So I know if I go to sketch a graph real quick, right, and maybe my y-axis needs to go a little further down. I know that I have an x-intercept at 0 and at 2. So then if I plug in 1, I'm going to get 1 times negative 1. So I've got negative 1 down here. And then I also want to find the intersection point. So I'm going to set 8 equal to x squared minus 2x. So that's going to give me 0 equals x squared minus 2x minus 8. And that factors to x minus 4 times x plus 2. So I already know that at, let's see, we've got, that's x equals 4 and x equals negative 2. And I lost my train of thought there. Okay. So I'm just going to extend this out a little bit. So we got 3, 4. So we have to go up to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to rescale this plot. This guy down here, there we go. Okay, so I know if they intersect at those 2 points, right, since the top function is up at 8, I'm going to draw that in blue. Maybe not if the iPad doesn't cooperate. Okay, so we know that we're going across at 8. Close enough to that being 8. Okay. So I know if we're intersecting at those points, right, I know that the y coordinates are going to be up here. And then maybe I want to plug in maybe f of negative 1. That's going to be negative 1 times negative 3. That's 3. And then f of 3 is going to equal 3 times 1. So that's also going to be 3. So we've got this nice parabola shape going on. And then we want to find, this is our region R. So we want to find the area between those two curves. No, I had it perfectly. Okay, we're just going to make that smaller. That way we can move it off to the side. Right, so the area between our curves, right, it's probably going to be easiest to do this as a vertical rectangle. So I'm going to just draw a rectangle in here so we can kind of visualize that. So because I have a vertical rectangle, I'm going to be doing it in terms of x. So my area is going to equal, my region's going to go from negative 2 to 4, because those are the bounds on my x-axis. And then my top function here is going to be 8, and my bottom function is the parabola, so x squared minus 2x. And then we're just going to integrate. So I'm going to distribute that negative. So we're going to get 8 minus x squared plus 2x. dx, that's going to be 8x minus 1/3 x cubed plus x squared, evaluated from negative 2 to 4. So if I plug in 4 times 8 is 32, minus 4 cubed is 64, so 64 cubed plus 16. And we're going to subtract, it's going to be negative 16 plus 8/3 plus 4. So then it's just a matter of simplifying correctly. So 32 plus 16 is 48 minus 64/3. And then negative 16 plus 4 is negative 12. Subtracting that, that's going to be plus 12 minus 8/3. That's going to give me 60 minus 72/3. And then 72/3 is divisible by 3. So 72 goes into 3 24 times. Sorry, backwards. 3 goes into 72 24 times, so this is 60 minus 24, which is going to give me 36 as my answer, as the area between the two curves. So the next example we're going to do is with a calculator. So we're going to let R be the region bounded between those two functions, so I'm going to go ahead and go over to my graphing calculator. I'm going to clear out what I just had. Okay, so we have 2x squared minus 6x, and then 3x minus 5. Okay, and then I'm going to make sure I'm on Zoom Standard. Okay, so I can see I have my parabola there, and I have my little line there. Okay, so I want to find the intersection points here. So my line is on top. So I want to find my intersection points. So I'm going to do second calculate option 5 for my intersection. I'm going to scroll over close to my first one. That is my first curve. My second curve, I don't guess. Okay, so my first intersection point is I'm going to label that as x1 over here. That is 0.649. Okay, so I'm going to show you a cool thing you can do in the calculator. I want to use that exact value from now on. I do not want to have to solve that again. So I'm going to go to my home screen. I'm going to hit second answer, so second negative. That pulls up the answer I just found. And then I'm going to store that as alpha A for my first starting point. So I labeled it as x1 over here, so I'm going to actually label that as A. And then my B value for intersection, I'm going to go back to my calculate menu, option 5. Now I'm going to scroll over towards the second intersection point, hit through twice, 3 times. Okay, so we get 3.851. Again, I am going to store that, so second answer, just make sure it pulls up the right number, looks good, store as alpha B. Okay, so now I want to integrate, so I want to find the area, and that's going to be the area from A to B. My top function was the 3x minus 5, and I want to subtract my 2x squared minus 6x. Now this is one that you could integrate by hand, we just can't evaluate it by hand. I'm just going to fix this because it bothers me when the dx is not on the end. Okay, so what we're going to do is that, oops, I don't know what that's about. So right, this is our y2 equation, and this was y1. So I'm going to go to the math menu. Function integrate is option 9. And then I want to go from A to B, so alpha A, alpha B. And then I want to do y2 minus y1. So I'm going to hit alpha trace. That pulls up my function shortcuts. I want to do y2 minus, another way to get those, if you don't want to use alpha trace and don't want to remember that, you can go to the vars key, hit y vars, function, and then y1, right? You can pick it that way as well. And our variables there is x, so I'll put that in, and then hit enter, and the answer key wanted it to the nearest thousandth, so I would say that is 10.939 units squared, right? It's area, so units squared. Okay. Right. So this one we also have a calculator for, and actually already gave you the picture just so we can kind of label it. So we have f of x is negative x squared plus 9, so I'm just going to highlight that in yellow on the graph. So that's our parabola curve here. And then we have the line negative 1.25x plus 8, right? And that's right there. So we want to find the area of the shaded region. So this is why I suggest drawing a rectangle, right? So if we draw rectangles, right here I have a rectangle, okay, so that's blue minus yellow, and draw another one that's blue minus yellow. But then when we get to here, right, this intersection point, right, the yellow curve, the parabola, is no longer on the bottom, right? So now we have these rectangles that just go from the line down to the x-axis. So we have two different regions here because there's a point where it splits up. I'm going to actually draw that line in black because it's hard to see with the lime green, right? There's a splitting point between where they go, right? So between where the top and bottom are the same, right? On the left side of that black line, the top function is the line g of x, the bottom function is the parabola f of x. But on the right side of that line, the top function is the line g of x, the bottom is the x-axis. So we need two intervals here. So I need to figure out where these intersection points are. So I can see here that this is probably a 3, but I need to know where those points are. So we are going to have to go over to our graphing calculator. And then let's see, f of x is negative x squared plus 9. And then I got negative 1.25, not 28, 25 x plus 8. I was getting ahead of myself in my head. So I'm going to graph that. Okay, so we are going to find that first intersection point. So second, calculate option 5. I'm going to scroll over towards that first intersection point. So that intersects at, I'm going to let that be my A value because that's my starting point, so 1.804. And I'm going to go ahead and store my answer as alpha A, right, and it pulls up that same number for me. So I know that it splits off here at 3 because that's where the parabola is going to intersect the x-axis. So then I need to know where the line has its x-intercept. So I'm going to go to second calculate 0, and I want to be on the red curve, so I'm going to hit down to switch equations. I'm going to scroll over so I'm to the left of where the 0 is, scroll to the right. 0 is at 6.4, right? Which we also could have just solved that. That's not a hard equation to solve, but whatever, right? So I'm going to store my answer as alpha b now. Okay, so then I'm going to go back over here for a second. So my total area is going to be, right, I'm going to let this be A, this is B. So for my first one, it's going to be from A to 3, right? And the top function is the blue function, so I'm just going to label that as g of x minus f of x dx. And I'm going to add that to the integral from 3 to b, and that's just going to be g of x dx, right? Because it's just the blue function over the x-axis, and since the x-axis is the line y equals 0, you don't have to put it in. So now I'm just going to type that in exactly as I see it. So I'm going to hit math option 9. I want to go from alpha A to 3. Let's see, and g of x is, I believe, in my second one. So we're going to hit, right, y2 minus alpha trace y1 dx. And then I'm going to do this all in one line, not even calculate them separately. And then we're going to add that to the integral from 3 to b. And then we're just going to do g of x, so that's just going to be my y2 here. And again, it's using the variable x. Hit enter, let it process. So we're going to get 9.481 units squared. Okay. I'm going to do one more problem, and I just want to show an example of when it might be helpful to use a dy integral instead. So we're going to let R be the region bounded by the function 2 square root of x and the horizontal line y equals 4 and the y-axis. Okay, so let's look at this. So we got, that's not a straight line. There we go. So we are bounded by the x-axis and the y-axis. So highlight that. The line y equals 4, 1, 2, 3, 4. Draw that in blue. Okay, so we have y equals 4. And then we have the function 2 square root of x. So at 0, that's 0. Okay, if I plug in 1, 2 times the square root of 1 is 2. And if I plug in, let's see, 4, I get 2 times the square root of 4 is going to be 2 times 2, so that's 4. Sorry, just spaced out on you there. Okay, so we have this curve, and we want the area bounded between the green curve, the blue curve, and the y-axis. So that's going to be this region right here. So here's R. So if we want to do this, we're not actually going to solve these. We're just going to set them up. You can always use the calculator to show that they're going to be the same exact answer. So if I first do this as a vertical slice, so vertical rectangles, I'm going to be using dx's. So my area is going to be from 0 to 4 on the x-axis. And then I'm going to do my top function, so that's the 4 minus the bottom function, which is 2 square root of x dx. But I might also want to consider doing it as a horizontal slice. All right, so draw a couple of rectangles just to kind of show it. So for a horizontal slice, horizontal rectangles, those are dy's because see how they're resting against the y-axis? So when we go to do those with the area, we want everything to be in terms of y. In this case, we're also going from 0 to 4 on the y-axis, so that's going to stay the same. This is going to be a dy equation. So notice that the blue line, the y equals 4 line, is not involved except to give us the top bound. So if I have the equation y equals 2 square root of x, if I want to do a dy equation, I need to solve for x. So I'm going to divide both sides by 2, so this becomes y over 2 equals the square root of x. So that means y squared over 4 is equal to x. So I'm going to set this up as just y squared over 4 and move my dy closer. So I'm just going to quick show you that these are exactly the same on my calculator. And because they're pretty easy functions, I'm not going to bother putting them in my y1 and y2 and stuff. So I'm going to do math 9. I want to go from 0 to 4. And I want to do 4 minus 2 square roots of x. And then we're doing that in terms of x. Okay, we get that number. And then I'm going to use an x as well for the other one just because I don't want to have to type in the alpha y every single time. But we're just going to change everything else. So 0 to 4. And then just going to, let's see, put a fraction in there. So that's going to be x squared over 4. And dx there, right? Those are just standing in place of y. Look, we get basically the same number. The issue up here with this first one is there's just, your calculator is using a numeric approximation mode. So it's just a little off. But see how like all the way out, right, we get the first 5 decimal places are the same. These are the same answer. And if you did them by hand, right, you can integrate these both by hand. You would be able to find the exact same fraction answers for both of them, right? So you get 5 1/3, so 16 over 3 would be your final answer.